I welcome you once again to this class of microscale transport process. What we have been discussing is various components of lab on chip. We mentioned in the last class that you need to have a pumping action, a valve action, a separation process going on, mixing, heating, detection, all these happening inside the chip. And there are some unique ways to accomplish these operations, particularly in microscale. What we have discussed in the last class is pumping, and then T sensor, then H filter, then detection methods, and then electrophoresis. This is one method which goes with electrical field flow fractionation. This basically separates a mixture of particles based on their size and charge. They band them in layers, and then these layers can be eluted in the way you want. The next item that I want to discuss today is known as dielectrophoresis. This is little different from electrophoresis. Here particles are separated based on dielectric properties, not their size and charge. Particles are separated in electrophoresis, particles are separated based on their size and charge. Here in dielectrophoresis, the whole idea is different. Here the particles are separated based on dielectric properties. For these, a non-uniform electric field is to be generated by the use of planar and point electrode. What that means is, you need to have a non-uniform electric field, and that can be generated by point and a planar electrode. So, that means one electrode is a point electrode and the other electrode is a planar electrode, and the electric field that is generated here, if we look at these electrical lines of force, okay, that is non-uniform, and when you are subjecting particles to this non-uniform electric field, more polarizable particles will be attracted to strong field region. See, there is a stronger field and there is a weaker field. There is a non-uniformity in the electric field. So, more polarizable particle will be attracted to strong field region. We will discuss the essential theories of this. I mean, what would be the force acting on the particle if you apply certain voltage, that we will discuss the theories of it. But for the time being, I want you to appreciate the fact that there are various methods existing by which you can separate particles based on their properties. Earlier we mentioned about electrophoresis, and I said that this electrophoresis can be turned 90 degree and can be used in conjunction with field flow fractionation. Here we have another technique which is known as dielectrophoresis, where the more polarizable particles will be attracted to strong field region. So, DEP can be used as a trap or in field flow fractionation mode. DEP can be used as a trap, okay, depending on properties, dielectric properties of the particles. Some particles can be held between the two electrodes, while others will be allowed to pass through that place. Okay, this is called a DEP trap. Or it can be, somebody can work on a field flow fractionation mode, where you have the upper electrode, and the lower electrode, and then you have laminar flow, parabolic velocity profile going in this direction. In that case, if the particles are oriented, if the particles are settling depending on the force balance at various locations, so they will be eluting at different time at the outlet. So, it can work as a trap, that means particle is held within this electric field, or it can be working on an FFF mode, that means particle is settling at a particular layer and would be eluting along with the velocity profile. So, in the second case, gravity acts against DEP forces in settling the particles at a particular height in the channel. In the second case means, in the case with FFF mode, that means in the case with field flow fractionation mode, the particle will be, if this is the particle, there would be a DEP force and then there would be a gravity force acting. So, there would be a balance between them, and wherever this balance is satisfied, the particle will be settling at that layer. And so, when you have this elution taking place, these particular layer, whenever it is eluting, which is governed by the parabolic velocity profile. So, whenever this particle is eluting, that I mean that will come at the outlet. So, here it would be a balance between the gravity force and the DEP force. So, in FFF mode, the gravity acts against DEP forces in settling the particles at a particular height in the channel. Live cells can be separated from dead cells by this method. That means, if some analysis is to be done where what type of cells are there, that has to be analyzed. Now, if the cells are dead or cells are live, that is important, because dead cells may not contribute to the disease when it comes to the I mean that is always there. People boil water to make sure that the cells are dead. So, this DEP by this method, live cells can be separated from dead cells. So, you know exactly what you are measuring, that you are measuring only the live cells. So, this DEP is also another dielectrophoresis, and DEP coupled with FFF, that is also one important operation that can be harnessed to accomplish a separation in micro devices. The next topic is electrical field flow fractionation. I said it is nothing but the electrophoresis, only it is turned by 90 degree. So, what I say here is top and bottom walls of the channel comprise of electrodes. Voltage is applied lateral to the direction of flow. Voltage is applied lateral to the direction of flow. Remember what the drawing that we have in the earlier class, we turned it 90 degree. So, you have one electrode here, another electrode there. Based on the size and charge, the particles will be forming a band. Particles will be, say for example, if these the system that is there, you have A, H and M components. These components are these A, H and M components. These components are, they belong to one particular band, because they, by virtue of their size and charge. So, they will be settling in one layer. Why? Because they, if this is a particle, this particle would be experiencing some electrophoretic mobility, right. The electrode is pulling. So, what are the forces? You have one force that electrodes are imparting on this particle, and at the same time, for this particle to move, there would be a drag force which is opposing it. So, if you put these electrodes for a particular time, okay, this particle will start moving, and if you freeze, if you switch it off, if you do not, I mean you apply the voltage and then you switch it off. So, by that time these particles will travel up to certain distance, particle of similar size and shape, they will travel up to certain distance. Particles of a different size and shape, they would be traveling probably a lesser distance or a bigger distance. So, these particles will be forming a band. One band represents particle of similar size and shape. So, this, if you on top of it, if you can apply a laminar velocity or parabolic velocity profile through this. So, at the outlet you will be eluting one layer at a time, first the central layer, then the other layers. So, if you have a pre-calibration done, you can using that calibration. That means, if you had a known sample going into it, and if you know when the components are eluting, so by looking at that calibration plot, you can compare with a real life sample and then say that okay, this real life sample must be having these components. So, what I write here is top and bottom walls of the channel comprise of electrodes. Voltage is applied lateral to the direction of flow. You understand that flow is moving, flow is going in this direction, and the voltage is applied lateral to it. Now, flow in particles with high electrophoretic mobility will pack more closely to the wall, that we understand. If the electrophoretic mobility is higher, that will go close to the wall. Flow in the channel is laminar and easily characterized, such as parabolic. Okay. Each layer moves at different velocity and particles carried by the layer elutes at different times from the outlet. We discussed this already. Slugs of particles separated based on their size or charge is detected at the outlet and identified based on prior calibration. So, this is exactly what I said. For the time being, you just, I mean, I want you to appreciate that these methods can be very handy when it comes to accomplishing a separation in micro devices. Okay. Now, essentially, I mean, if you are interested in the theories, I mean, what force we are talking about, what would be the drag force, we will come to that very soon. Now, I said that this filled flow fractionation, this is a very unique treatment, that layers are moving, sliding one against the other, and we are relying on it. We are assuming that if there is a cross flow, if there is some eddies forming, then this whole idea is, you should throw in the dustbin. It is absolutely of no use, but you are practically, you are relying in a very significant way the flow of two layers parallel to each other, and only diffusion can take place between the two layers, and one layer is sliding against the other. Now, there are other modes of filled flow fractionation we discussed. One is flow FFF, flow filled flow fractionation. Here we have use of transverse flow with membrane attached to wall, right. What we had there is a transverse flow with membrane attached to wall. Concentration polarization directs the particles to settle in a layer depending on the diffusivity, in turn the size, right. This we briefly discussed in the last class, that you have the bottom, say bottom wall is the membrane. So, in that case you have particles plus some liquid, some salt, say water, and some other particles in water. So, water would be flowing through the membrane and the particles will be held next to the membrane. Now, the bigger particles, it would be difficult for the bigger particles to diffuse back to the bulk, whereas for smaller particles it is easier to go back to the bulk. So, there is something called a polarization happening, and so the particles will be forming bands depending on their size. Okay. And then if you impose a velocity, if you impose a parallel, if you impose a parabolic velocity profile, what you find at the outlet is that each layer will be having, each layer would be representing diameters or particles of certain size. So, against some pre-calibration, you can always check, you can always confirm what all particles were present in the system. Similarly, you can have a thermal FFF. There the bottom wall and the top wall, they are at different temperatures. Okay. So, diffusivity is a function of temperature and particle size. So, if one of the channel walls is hot and the other wall is cold, thus creating a thermal gradient across the channel, then you can accomplish this thermal FFF. Now, here higher molecular weight particles compact more tightly against the cold wall than do lower molecular weight particles, and again because of laminar velocity profile of the carrier, lower molecular weight samples will have higher average velocity and elute before higher molecular weight samples, resulting in a fractogram. Just exactly same method, you are playing with velocity, parabolic velocity profile, one layer moving against the other, and one layer is moving at a higher velocity or a lower velocity compared to the next layer, and at the same time you are creating a gradient in lateral direction. You are putting the particles of different sizes, different charges at different layers, and so you are eluting at different time, and against a pre-calibration, against, I mean, you run a known sample, see when you see those particles coming out of certain sizes, and then compare that with a real life sample and put one against the other and compare and see what you have. We discussed this valve action, okay, and we said that there are certain ways to accomplish a valve action. One could be the valve made of hydrogel, and another is valve made of hydrophobic layer. Of course, there could be valve using a mechanical using a system similar to a mechanical valve. That means, there is a valve seat and there would be a piston coming, which would, when it hits the valve seat, then you consider valve to be closed, or it can move allowing the flow to take place. So, these are some of the things you can accomplish in micro scale, but it may not be very easy to accomplish, and we should be looking out for other alternatives that are available in micro scale, and that alternative is this valve made of hydrogel. What you have here is, suppose you have a channel like this. Okay. You have a channel like this and you have pillars placed here. You have pillars placed here. So, or these are called posts on the channel with hydrogel jacket around it. So, you have a post with hydrogel jacket around it. Okay. You are having a flow taking place and you want to, when you want to see that when you desire to have a flow through this channel, that should happen. All right. So, what happens here is hydrogel in its expanded state block the channel. So, this hydrogel layer can contract or expand, that means it can shrink or it can grow. When it grows, it blocks the channel, and when it shrinks, it opens a part of the channel. So, contracted hydrogel allows the flow of fluid down the channel. Now, how will you accomplish this contraction and expansion? That can be done by an external trigger, because hydrogel has some unique properties. It responds to external triggers such as pH or thermal environment. So, that means if you increase the temperature around, it shrinks or swells. This is a unique property of a hydrogel. So, this property can be utilized particularly when you are working with a micro scale geometry. Now, here the response time of course is very critical. How quickly it will respond, because fractional change in diameter should reach 1.0 within seconds. That means, if you plot fractional change in diameter with time, fractional change in diameter, so the final diameter is say 1.0, that is when you consider this to be closed. Okay. So, that is the place, that is the point when you consider this to be closed. So, with time you will find that the diameter will change. Suppose it was in a contracted state, and then you suddenly you put the trigger. So, the moment you put the trigger, you start measuring what is the fractional change in diameter, and you would like to reach 1.0, because when you reach 1.0, that is the point when the valve would be completely closed. So, these should be you should accomplish this within seconds, then you consider this response time to be good, right. Because you put the trigger and immediately you should see the change, because this is a chemical or physical chemical property you are utilizing. So, if you put the trigger and the response it takes place for half an hour, then of course, this is not going to work. So, it has to act within seconds, then only you can consider this to be good. Now, there is an article in Nature. In fact, people have worked with different materials where you can accomplish, you can reduce this response time. And another important point is time response can be tailored by selecting the right number of posts and the thickness of the hydrogel layer. See, you have a choice of number of posts and what thickness of the hydrogel layer you want to pick up. Now, you should choose it such that it matches the response time, so that the valve gets closed within seconds. All right. Suppose, I mean, you got my point. What I'm trying to say, the number of posts that you have, the thickness of the gel layer, all these things are in your hand. So, you would be playing with them as well, and see the fractional change in diameter, and then you come up with the best design. Then this other idea that is there, valve made of hydrophobic layer. It is basically something like this: a liquid being unable to expand freely forms an interface with second liquid or gas. That is basically the essence of surface tension. If interface is curved, there is pressure difference across the interface. The pressure is higher on the concave side and the pressure increase is balanced by surface tension forces. How would I put it here? If I have a hydrophobic layer, and if I have say flow of water taking place, how would the meniscus look like? The meniscus will look like this. The meniscus will look like this, right? If it would have been hydrophilic, then it would have been advancing, but since it is hydrophobic, it is in other direction, right. So, the interface is curved and there is a pressure difference across the interface. So, this unless this threshold pressure is applied on this side, you may not see this fluid entering into this hydrophobic into this capillary with hydrophobic wall. Also, so a flow to take place, the applied pressure gradient has to be greater than the capillary pressure. Also, an abrupt change in the width of the channel causes pressure drop at the point of restriction. So, by adjusting the width and height of the channel at the constriction and with wall coating that provides adverse contact angle, it is ensured that flow can take place only when pressure at upstream side exceeds pre-specified value. What is the formula you have there? If this is the angle it makes, suppose this is the angle it makes, okay, then in that case, and if you have an abrupt change in the width of the channel, that means abrupt change in the width of the channel means you have, suppose you have the channel which is having an abrupt change in the width. So, this was the original channel, this was the channel, right. So, this was the channel and you are pushing the liquid through this channel. So, in that case the delta P, the pressure difference that you have to provide is given as 2 sigma L cos theta c into 1 by W1 plus 1 by H1 minus 1 by W2 plus 1 by H2. So, this is the pressure drop that you have. This is the pressure difference between the liquid menisci. So, this pressure, and what, of course, you will ask what is W1 and H1. This channel is considered having a width W and height H. So, this channel is not exactly a circular channel. This channel has width W and height H, and other channel is, so one is W1 H1 and the other channel has W2 H2. Okay. So, these are the dimensions of the channel. Theta c contact angle and sigma L is the interfacial tension. So, this is the formula. This formula is very similar to the one you have seen, you remember, for a capillary rise you had this what was the formula, pi dn sigma, where dn is the diameter, or if d is the diameter of the capillary, it is pi d sigma cos theta. So, it is a very similar formula. It is a very similar formula, only thing is here you have a change in abrupt change in width of the channel, and that is reflected here. So, here this is the pressure drop, and this pressure drop you have to overcome if you want to have flow through this channel. All right. So, you can set your system in such a way, I mean you have what W and what H you choose, that is in your hand. What material, what theta c you choose, that is in your hand. So, you choose these materials in such a way so that these acts as a valve. When the pressure exceeds this delta P, then only there would be a flow, and if it is not, there will be no flow. So, if you want this branch to have flow, you have to go to that delta P, otherwise the flow will take place. If you have a parallel branch, it will go there, but it will never enter through this one. Okay. Similar concept can be used for flow splitting. So, this is one way you can play with the hydrophobic layer to accomplish the valve action. Then this we discussed about mixing. You remember that mixing would be an essential part, because you are introducing a sample, and very importantly that sample has to mix with the reagents. That sample has to mix with the reagents. So, and then how it responds to certain reagent, that you are checking in the detector. So, that is how a sensor will work. Now, mixing is a very integral part of these microsystems, and not only for lab on a chip, mixing would be a very integral part for any micro scale operations. Now, this you can always have active mixing, you can always have a moving component, just like the impeller in a pump. However, you should be looking for alternative routes, and people have already looked into these. They have come up with something what is referred here as passive mixing. What you have, you look at this channel, here at the bottom wall, this channel has grooves. This channel has grooves in the bottom wall. So, when the flow takes place, suppose the two streams are coming from two sides, and you expect the two stream to mix. So, as the two streams enter into the channel, these grooves at the bottom, at the floor of the channel, these grooves will ensure that some fluid flows through this groove. Some fluid flows through these, some portion of the fluid flows through this groove, and when it flows through this groove, what it will do is, on the way it will drag the fluid which is above it, right. If one layer is moving, then by viscous action the next layer will move, may not be at the same velocity, but at a lower velocity, then the next layer would be moving also. So, when a fluid moves, when a fluid goes through this channel, it will pull some of the fluid above it as well. So, you will be inducing cross flow through this channel, that is the idea, that you have this channel, you have these grooves placed in the floor. So, you are intentionally inducing a cross flow. Okay. Why do you need such cross flow? I mean, after all, a diffusion will ensure that there is a mix. If two layers are flowing side by side, you know that there would be diffusion, and that diffusion will ensure that there is mixing taking place, and if they are immiscible, then they will never mix. So, what is the purpose of having this having this cross flow? The idea here is that when two layers are flowing side by side, there would be diffusion, but the diffusion will take place only through certain contact area, that is the contact area between the two layers, right. So, that is that contact area through which the diffusion takes place. Your objective here would be to increase that contact area, so that enhanced diffusion can take place. If the two layer flow side by side, everybody knows there will be diffusion and some amount of mixing will take place, but that mixing will take place only over that contact area. But if somehow you can increase the contact area, so that is the idea here. So, the two streams are brought one into the other by having a cross flow. So, that is the purpose of the groove, that it will bring one stream will be brought into the other stream, and they will intermingle. You can have such in fact, in a conventional static mixer, you have baffles, probably the purpose is very similar. Okay. Now, of course, one issue there would be, if you are having a turbulent flow, then there would be you will be having all kinds of eddies present. You know, eddies arising due to turbulence. That is not happening here. This you are very much inside. You are having a low Reynolds number, and you are very much inside laminar flow. However, you are introducing some amount of chaos in the flow by these methods, by these grooves. So, these grooves are encouraging cross flow. So, one groove is encouraging a flow in this direction, and the other groove is encouraging flow in this direction, right. So, these flow will go and hit the wall, and then again it will come back, and so there is a swirling taking place. in this direction as well as in this direction. Now, what you will find here is beyond certain distance, this is changed. These were say 2/3. See, one side is longer than the other. You must have noticed. Okay, one side is longer than the other. So, if this is 2/3, then this is 1/3. So, what you are doing essentially is, if this is the one you have, and half of the stream was A and half of it is B, and they are fed into the channel, then this groove is basically starting, one groove is starting from here, and that is the groove, and the other groove is in this direction. So, you are basically swirling, you have taken 2/3 and you are swirling here, and 1/3 you are taking and you are swirling here. That is what you are trying to accomplish through these grooves. Beyond certain distance, after how many, 1, 2, 3, 4, 5, beyond 5 grooves, you see the pattern changed. Here it is, this part is 1/3 and that part is 2/3. So, earlier you were swirling with 2/3 portion of this. Now, originally your system was, originally the fluid that has entered there, that was half and half, that was splitted half to this side and half to that side. However, you started working with 2/3 on this side and 1/3. So, you picked up a certain portion from this and you are putting it into the other stream, and then it got, after the 5 such grooves, then you are reversing the flow pattern. So, by this way you are having cross flow, then again moving in the other direction. So, at the end of it you are accomplishing a thorough mixing, that is the whole idea. So, diffusion between two parallel streams in laminar flow, enhanced interface between the streams, that is the idea of passive mixing. You have enhanced interface between the streams. Two streams are allowed to intermingle, brought close to each other, and then depart from each other due to baffles in the channel. So, two streams are allowed to intermingle, brought close to each other, and then depart from each other due to baffles in the channel or due to these grooves present. Cross flow between two streams is induced by inclined grooves. Now, this is a typical concentration profile that you see here. This red and blue color, these are two extremes, say concentration in some unit. Blue, extreme blue represents 2.88 into 10 to the power minus 6 here, and 6.2 into 10 to the power minus 3 there. So, these are the two extremes and they are going through the inlet. So, this is the inlet, half of it occupied by red and half of it occupied by blue, and as it flows down you can see that it is getting mixed and it is coming at the end of it, it is coming almost green, which is halfway between the two concentration. So, that is a typical that is how a passive mixing will work. Now, how to characterize this mixing? How would you know that you should have 1 millimeter length of the channel, or maybe 2 millimeter or 0.5 millimeter? How will you decide? I mean, 1 millimeter you accomplish some mixing, but whether it is a complete mixing, because it will never, you will never have a complete, you will have complete mixing beyond certain distance. Okay. Now, you could have stopped here itself, you could have stopped, you could have stopped here itself. Here also you had mixing, but you had some amount of deviation also. Say if we put average as 0.5 and extremes are 0 and 1. So, here you have a deviation, here you have a deviation, here you have a deviation. However, that deviation is between say 0.7 to 0.3, right. It is, that deviation is not here. If you look at this, deviation is between 0 and 1. So, this is considered completely unmixed. Here there is a deviation, I mean halfway down the line, if we see there is a deviation. However, that deviation is between this deviation is, I mean I am talking about this place where the cursor is, this deviation is between say 0.7 and 0.3. So, so there are ways to quantify it. What is the mixing, how much mixing have you accomplished, and whether you consider this to be acceptable or not, and up to what length you should have. So, how this extent of mixing varies with length. So, all this kind of analysis people have done, and we will discuss this down the line. Okay, this is all what I had as far as this lab on chip is concerned. The next topic that I would like to get into is basically microfabrication. Um, I will spend a few classes on the basics of microfabrication, and then I will go to the essential theories of various operations that we talked about now. For example, electrokinetic pumping and all. So, those we will get into after this discussion on microfabrication, because first you need to understand, I mean, we have said that yes, we can do in micro scale, we can do field flow fractionation, or we can do electrokinetic pumping and things like that. However, first, how would you accomplish this practically? How would you make a micro scale device? So, I think it is essential that I spend at least a few classes on this, what are the tools that are available in microfabrication. When we look at fabrication accuracy, what we see, these are some of the scales that we have here. A city, the fabrication accuracy is 10 kilometer, house it is 10 meter, optical fiber one, I mean these are the not the fabrication accuracy, these are typical length scale that we consider. Okay. A house, okay, where is the house located, and if you say within 10 meters where the house is located, you will be just fine. Whereas, where the optical fiber is located, if you can say within 1 millimeter, I mean it is that way. So, length scale is important, where about, I mean what your objective is, the length scale also varies. Okay. Similarly, you have the dimension of bacteria, virus, and all the way going to 1 angstrom, I mean that is the final one. I mean not the final one, but that is something which we are aware of. Okay. Traditional mechanical machining is the one that we have in the workshops. You must have studied in a workshop, there is, it commonly goes by lathe machine. So, this traditional mechanical machining, they operate on objects of size 1 millimeter to 50 centimeter. Okay, 1 millimeter to 50 centimeter. If you go to a workshop, and if you go to a lathe machine, these are the typical objects they have. I mean, if you measure the objects that they are working with, these are the typical objects, and precision of the order of 10 micrometer. It depends on what type of machine you have, but if you go by the route of mechanical machining, typically that is the best precision that you can have. Then you can have what you call a special mechanical machining, that is possible. The special mechanical machining is these can have a displacement precision of 1 nanometer, angular precision of 10 to the power minus 5 degree. This is applicable for metal alone, not for glass, Teflon or plastic, and most importantly this special mechanical machining, they have a high price tag. So, these are, I mean you can always say traditional mechanical machining, that has a limitation in terms of precision. So, when it comes to doing it in when it comes to making a micro scale device, traditional mechanical machining may not work. One can go for special mechanical machining, and this displacement precision etcetera, these are there. This special mechanical machining can be used, only thing is it is generally not applicable for glass, Teflon or plastic, it is mostly applicable to metal, and it has a price tag. So, these are some of the disadvantages. However, when it comes to accuracy, this special mechanical machining can deliver what you want to accomplish in a micro scale device. On the other hand, what people have what is done here is the techniques that are used in semiconductor industry, for example, etching, lithography, deposition, these techniques are borrowed to develop micro scale devices. I am going to discuss, because this etching, lithography and deposition, this is something new to you. I will discuss briefly what these techniques are about, but I would like to point out here that here the range is 0.2 micrometer to 500 micrometer, and the use of glass or silicon is there. you can use glass or silicon. So this etching, lithography and deposition, this technique can be used for microfabrication. These are primarily used in semiconductor industry and these are borrowed from there and these work just fine. There is another important component of microfabrication. I mean, we said that you can use etching, photolithography, these techniques for silicon and glass. Now, silicon and glass, these are one of the major the micro devices that are made. Mostly these are made in glass and silicon. However, a very important class there is plastic MEMS, the micro scale devices which are made of plastic instead of glass or silicon. The primary reason is that these plastics can be really cheap and it can be disposable. So, it can be made, use and throw away, and so when it comes to making a sensor which will be used for once. So, you put a sample and then you do not want to know what sample has been adsorbed in some place. So, you do not want to reuse it. So, you have to throw it off. So, you want to have something which is degradable and which is cheap. So, these plastic devices, plastic MEMS, they come under that category. Plastic devices, these are made in a, I mean these devices cannot be made using photolithography. However, there are other methods which we will discuss very soon. Now, the range is 0.5 micrometer to 500 micrometer. Use elastomers such as PDMS or PMMA. These are the two elastomers which are very common, polydimethyl siloxane and polymethyl methacrylate. These are two very important plastic materials which are used for microscale devices when it comes to making it in plastic. Channels can be made by either direct method, which is laser ablation, or replication method, use of mold. Use of mold is you make a negative of it by in silicon or in metal, okay, and then you pour the plastic material onto it, and or you make a stamp out of this make a negative stamp from metal or silicon, and then you heat the plastic material so that it becomes soft, and then put the stamp and apply some pressure, so that the stamp gets engraved on that plastic. So, you make a channel, a negative of a channel. Negative of a channel would be a raised portion, right. Negative channel means a dip on the surface. So, negative of it would be a raised portion on the surface. So, that negative if you put on a soft plastic, so that will create an impression which would be a channel. So, that could be a method. Primarily that method is used for PMMA, because PMMA has higher melting temperature. On the other hand, PDMS has low melting temperature. So, PDMS you cannot do that way, or so what people do is they melt the PDMS and pour it on the mold. You might have already studied molding, that you have the negative sitting there and on that you pour it, you melt it and then you pour it, and after it gets cooled down, then it comes out, you just peel it off and you get the positive. So, that is exactly the method that is followed here. Channels can be made by either direct method, that is laser ablation, that means you take the plastic material and then you selectively remove a portion which will form the channel. So, you take a plastic plate and then selectively remove a portion using laser ablation. That is one method, but that is not that direct method is not followed in general. I mean, if you go through, if you read the books, you see that these are the replication method is more common, where you have the mold, where you have the negative, and you either pour the molten polymer or soften the polymer by application of heat, and then take the stamp which is the negative and then press it, so that you get the channel made. By weight, plastics are 100 times less expensive than silicon and can be made disposable. That is the advantage that you want to take when it comes to use of plastic. Other important thing is rapid prototyping. Suppose you have to make 100 chips within a short time. You want to make large number of such devices, because if it is a use and throw away system, so it is it has to be made in large numbers, and in industrial scale it is much easier to work with plastics. And there are other effects that you can introduce, such as surface effects. Plastic can have surface effects can be induced to it. For example, it could be hydrophilic, it could be hydrophobic. It is hydrophobic, but if you treat it with plasma, it becomes hydrophilic. So, things like that. I mean, you can have lot of chemical, if you oxidize the layer, then you have one property, then if you do not, then you have another property. You have those fantastic properties available with the plastic material. And one very important thing is transparency, particularly if you are going for an optical detection, transparency is very important. You can see what is going on, you can pass the light through it, or you can detect light that is emanating from it. So, this is very important, and diversity of materials can be introduced easily. So, these are some of the plus points of plastic MEMS. Of course, there are negative points, I mean nothing comes free. Plastic, of course, there is a problem of aging. If you have glass, you know glass will stand the test of time, but plastic after some time it may age. And if you want to make something which has a high aspect ratio, that means very thin channel, but very deep, it could be possible that you press it, I mean this channel may not maintain its aspect ratio. So, there are issues which goes on the other side of the balance as well. Now, before we get into this microfabrication process further, I must tell you, you have heard of clean room, this that you have to have a clean room to do microfabrication jobs. Now, I would like to define, I mean if you go to a definition of a clean room, what we see there is that the temperature has to be regulated at 20 degrees centigrade, and humidity regulated and traversed by flux of filtered air. Then how do you define a clean room? You must have seen, you must have read the clean room of type 1, clean room of type 10. So, what is that number? Number of particles of size less than 4 micrometer per cubic inch defines a clean room. Number of particles of size less than 4 micrometer per cubic inch defines a clean room, and the number that is given for a clean room, if it is less than 10, that is typically suggested for a microprocessor, fabrication of microprocessor, whereas for MEMS microfabrication a number less than 10,000 is suggested, and if it is less than 10,000, typically wearing hair cover, shoe cover, gloves etc. are required. So, what this means is that the clean room that is required for microfabrication of MEMS device, that may not have to be same as the clean room that is required for fabrication of microprocessor, and still for microfabrication of MEMS device you need certain cleanliness, and that requirement is here, the wearing hair cover, shoe cover, gloves etc. these are required, and of course, the other conditions have to be satisfied. One thing I would like to point out here is that typically the replication method, when you make the mold, when it comes to making plastic MEMS device, when you make the mold, clean room is a must. I mean when you take because you have to make a silicon master. You have to make a master which either you press it as a stamp or you use it as a mold on which the liquid molten plastic would be poured. Now, when you make that master, it is important that you have the clean room, but when it comes to the replication method, the requirements are not that stringent. That means, when you are pouring it or when you are pressing it on the plastic material, the requirements are less stringent. That is what I understand. I mean that is what written in references. The other topic, I mean as we go into this etching process, I said we do not. So, what we are going to do in this course is I am not going to discuss about the that special micromachining, because traditional micromachining and then more efficient, more precise special micromachining, these are already there. I am not going to discuss that. What I will discuss is the etching and the photolithography and those steps which are, as I said, are borrowed from the semiconductor industry. Of course, borrowed mean a sense that you make it work for microscale devices. So, whatever technique I mean you take the essence of the technique and then make the appropriate changes, so that it suits your requirement. So, that etching and photolithography, that particular technique, I mean if I want to repeat, I must say that we are not talking about traditional machining or special mechanical machining, though these are there. We are focusing on etching, lithography and deposition, this particular technique. Okay. And what we will point out here is that this etching, lithography and deposition technique will be used to make microstructure device with glass or silicon. Okay. And then that device, we can make a positive in that device, we can make the negative as well, and these device would be used to make a master for plastic MEMS. All right. So, we are primarily focusing on this, that means we are primarily focusing on etching, lithography and deposition, and then we will study how we can pour the plastic material, or how we can create that, how we can this method is known as hot embossing. That means, you soften the plastic and create a stamp and put some pressure. So, how this hot embossing is done, that we will discuss down the line, but we are not going to take up this traditional mechanical machining or special mechanical machining. So, we briefly point out, I mean I do not I will probably get into this photolithography process at a in the next class. What briefly we point out is that there has to be a mask, and there has to be a light source. So, light would be on the top, okay, and then there will be a mask. Mask means a certain portion is black and certain portion is white, okay, and below the mask there would be the wafer on which you want to create the channel, and you coat that wafer with a photoresist material, with a photoresist, which is basically a polymer. Okay. This polymer has some unique property. If light is shining on certain portion of the polymer, those portions will become soluble in certain solvent. So, these are photosensitive polymer, these are called photoresists. So, on the wafer you have this coating of photoresist, and you have a mask. On certain portion it is dark and certain portion it is light, certain portion is dark and certain portion is white, I mean certain portion is transparent and certain portion is not, and on top of that you have the light. So, as the light shines, so light will travel through the transparent portions, but it cannot go through the covered portions, the portions where through which light cannot travel. So, it will go only through the transparent portion and it will hit the photoresist, which is the coating basically on the wafer. So, it will hit the photoresist. So, it will make those places vulnerable, all right, wherever light hits. So, those places are vulnerable. So, you dip it in a solution and those portions will be solubilized. So, solubilized means it goes to the solution. So, those portion gets exposed. Now, you add a etching chemical, now you add certain chemical which attacks those places, chemical attack, chemically react with silicon, if it is silicon, and that product goes to the solution, product does not stick to the surface. So, if you dip it for say 1 minute, you will see some etching taking place only on those exposed portion, the other portions remain as it is, because it cannot penetrate the photoresist, all right. And then when you are done, you remove the photoresist finally by some method. So, you have those channels engraved on the wafer. So, this is essentially what is photolithography, but I would this I said I mean I did it in a very cursory manner. I would discuss this in detail in the next class, how the photolithography takes place. That is all for today.